Hello. So my name is Kumar Saurav, and I am a PhD student at TIFR Mumbai. So today I will be discussing my PhD work that I have done in last 5 years. So and these are on age of information scheduling problems that I have done under the guidance of Professor Rahul Baze. So let's begin. Um, so in past we have considered several scheduling problems concerning generic communication networks where we have say multiple sources. Uh, at each source, packets arrive intermittently, and the sources need to transmit these packets to the monitor. And for each packet, we define latency as the time difference between when a packet arrives at the source and when it is received at the monitor. And the objective is to schedule at any time which source should transmit which packet, such that the sum of their packet latencies is minimized. um, okay. uh, but however, consider modern applications such as virtual reality. Here you have a source and a monitor, and it is required that the information at the monitor should accurately reflect the most recent state of the source. So this is called information freshness. Naturally, this information freshness has to be achieved by transmitting a sequence of updates from source to monitor. However, here the emphasis is on the recent information at the monitor instead of the individual updates that are transmitted from source to monitor. So this is basically this problem is difficult to model using classical metrics such as latency, and hence these metrics are not sufficient to study information freshness. Hence different approaches have been followed to formalize information freshness. Most popular one being using this age of information metric. So this my thesis is basically about my PhD work is about this age of information. And so what is this age of information? So basically consider a source monitor pair, uh, and at a source let update is generated at time g1, which is received at the monitor time r1. Another update generated time g2 is say not transmitted. And another update uh, is generated at time g3, which is received at the monitor time r3, and so on. At any time t, look at the latest received update, look at when it was generated at the source, the difference between its generation time and the current time t. This is the age of information at time t, right? So mathematically, this is given as follows. So by very definition, this age of information increases linearly with time until a new update is generated, at which time this age of information decreases to a value that depends on the generation time of the uh, received update. And then again, it increases linearly with time, and so on. So broadly, we can say that this age of information quantifies how old the latest information at the monitor is. So this is the idea of age of information. So for information freshness, what we want is that the age of information for each source remain low. So what is the problem here? Basically, at any time, you have a limit on the number of sources that can transmit simultaneously. So which source should transmit and which update the source should transmit, uh, and how much energy to spend for this for transmitting this selected update. Um, so throughout this talk, I will use update and packets intermittently, so without any difference in their meaning. So please bear with that. So these decisions actually depends on different factors. Uh, some of them are like the network topology, basically, or the how the energy is consumed, how much energy is required for transmitting packets, and uh, based on that. So how the network, basically the network topology, it determines what kind of scheduler we can use. One is say is a centralized scheduler, where there is a single scheduler in the network which is aware of all the state of all the others, all the sources, and it basically decides which source should transmit at any time. And the another one is a decentralized scheduler, where each source basically has to decide on its own whether it wants to transmit or not at any time. So there is no centralized scheduling, unlike the previous case. So here there is no coordination among the sources, and hence there can be packet collision if multiple sources transmit simultaneously. Another is, as I said, energy consumption model. So how the energy is consumed upon transmission. So first is one is tunable energy consumption. Here basically you choose you at what rate you want to transmit, and accordingly you will consume power and hence energy. So you want to transmit at higher speed, you consume more energy. Uh, like greater speed or transmission rate, I mean, that will help you minimize your age of information. You can transmit more updates like at a faster rate. However, again, like you have this energy cost. The other one is this fixed energy consumption model. Here, the speed cannot be controlled. The transmitter transmits at a fixed speed. Basically, you can just choose whether or not you want to transmit. So you can't precisely control the speed. Um, so here, like you consume like fixed power, and so in my PhD work, my PhD work can broadly be classified into four parts based on these different scheduler types and energy consumption models. So first part, I will so in the following video I will discuss these four parts. The first part will consider a single source. Um, uh, like first we will consider single source and analyze it for both tunable energy consumption model and fixed energy consumption model respectively. And like single source, there is like only this centralized setting makes sense. So um, then we will go on to multiple source setting. Here we will like only focus on the fixed energy consumption model and analyze it for both centralized and decentralized setting. So basically, we will have like four parts to this presentation. So first part, single source tunable energy consumption model. So you have a source monitor pair. Updates are generated at the source at arbitrary time instance, uh, and all updates are of fixed size. So for now, we make this assumption that the sizes of all the updates are fixed, W bits, which is known in advance. This age of information decreases when all W bits of an update are received at the monitor. That is, when entire update is received, like when an entire single update is received at the monitor, then then the age of information will decrease depending on its generation time. And the source has variable rate transmitter, so it can control the transmission rate, and accordingly it draws power. It can control the transmission rate. Large transmission rate will help you minimize age of information, while low transmission rate will like be bad for age of information. Uh, so basically, this when you transmit at large transmission rate, you have this low age of information, but also you consume a large power. So how is that? The source has a packet to transmit of W bits. It chooses at what rate it wants to transmit, and accordingly it draws power. And this power is a function of the speed, and this power function is an increasing and convex function speed basically. So for example, it can be of the form s square, or basically a polynomial or exponential. So basically it increases with speed and it is convex. So the problem. So what is the problem here? That at any time we want this age of information to be less than a certain fixed threshold d. and uh, so we need to ensure this, like that the age of information remains below uh, D uh, while consuming minimum energy. So this is basically an online decision problems. You don't know when the updates will arrive, and you have to at any time schedule which update you want to transmit such that this age of information remains below D, and the energy consumption is also minimum. So what are the decision variables? Like broadly, you can see at any time which update to transmit and the speed for transmission. Um, but we will come to this to understand it well. Let's consider the following example. Like you have like two updates, like one generated time t0 and one at time t1. Now let without like assume that without transmitting this update, the first update at time t0, you directly transmit update t1. You finish like transmitting it at time t2. Now, so now beyond time t2, you see that you don't need to transmit the first update because this age of information only depends on the generation time of the latest transmitted update. So this is like basically like so all previous updates, once you transmit the latest update, all previous updates are useless. So first the first point, that all updates need not be transmitted for age of information minimization. Further, like this age of information, we saw that it increases linearly with time unless you transmit a new update. So once you have transmitted this update generated time t1, you know that if you don't transmit any further update, at some point in time, this age of information will increase this threshold d. So you know how much time you have before which. So before this time, you need to transmit an update. So now this means two things. Look, first, that at least one new update must be generated before the age constraint, the peak age of information constraint is violated. And the second, that the source must completely transmit this update before this time. Right. And so the first point, the like update generation, we don't control it, but we assume that uh, there will always be an update. So basically, what this means is that we assume that the intergeneration time of updates is less than d. So basically, before this age of information like exceeds d, you have a new updates. So this is a feasibility condition. This is a necessary like condition. We assume this to be true. The second is the source has to like completely transmit. So this is under our control. This is what we need to ensure. So what this also means, like if you look carefully, what this third point actually means is that this is a deadline constraint. So after you have transmitted this update T1, um, generated time T1, you know when the age of information will exceed the threshold. Before this time, you need to transmit. So this time, this T1 plus D, this is a deadline. Basically, you have to transmit an update before this time. Um, so at any time T, like you know how much time is left before this like constraint will be violated. Um, so before that, you have to transmit this new update completely. So basically what I want to say is that this peak age of information constraint is equivalent to a deadline. At any time t, you have a deadline before which you need to transmit. When you transmit, this age of information will decrease, and then again you will have a new deadline before which you need to transmit. Now, having like understood this deadline constraint, let's understand what are the like trade-offs, like which update to transmit at any time. So in previous example, like we had these two updates T0 and T generated time T0 and T1. So which update should we transmit? So let you have a update here at time T1. Um, you know the deadline. You need to transmit this update one update completely before deadline. You don't need to transmit update one. You need to transmit some new update before this deadline D1. Now, because right now you only have update one, so you need to transmit it. Say you begin to transmit it and at time t2 you have some bits, like out of these w bits you have few bits left. And now say at this time another update is generated. So as I said, before this deadline d1 you need to transmit some update completely, some new update completely. So now you have these two um, updates. So which one to transmit? So let's say we just continue to transmit this update one, uh, update one. So basically there are fewer bits of update one. So you can transmit it like at a lower transmission rate and consume less energy. However, see now the update one is already old, right? So the next deadline will be close, right? It's T1 plus D. Um, so if a new update is generated, then you will have to, like, you may have to transmit it at a very large rate. In contrast, if you switch, if you just discard this update one at time t2 and begin to transmit update two directly, then it has more bits than update one and the deadline is identical. So you will actually have to transmit this update two at a larger transmission rate to complete it before time d1. But then the next deadline will be um, like far ahead. So to transmit the next update, you will have more time. So um, you can transmit that update at a lower transmission rate. So basically, this is the trade-off, and you need to choose at any time which update to transmit and the transmission rate. What is the uh, goal here? That we want to find a policy for, like, basically you don't know when this update will be generated in future, and basically the actions like the energy consumption, it's all related, which update you transmit now and when the next update is generated. So basically in this case, like finding an optimal policy, like the best policy that consumes minimum energy, that is uh, difficult. So we consider an alternate problem where we need to find a causal policy which has like least competitive ratio, which is basically to say that regardless of what the input is, my performance is close to what the best algorithm can do. I'm coming to the definition of competitive ratio more formally. So basically, this competitive ratio is a metric to for like causal policy. Um, Basically, how the performance of a causal policy. So let sigma denote the update generation times, like when the update will be generated in future, this and the sizes. So in this case, like it is fixed, but in general it can vary. So um, this is not known to causal policy in advance. Like it does not know. A causal policy only knows has past information, uh, does not know about the future. And now for this given input sigma, we define this cost function, like cost incurred by any causal policy by, and the second one is the cost incurred by an optimal offline policy. So what is an optimal offline policy? Is a policy that knows the entire sequence of packet generation times and sizes, and then it minimizes the energy consumption with this information. For causal policy by its competitive ratio is defined as the ratio of the cost incurred by this policy divided by the cost incurred by an optimal offline policy maximized over all possible input sequences. This is a competitive ratio, and our goal is to find a causal policy with least competitive ratio. So in this considered problem, this cost is basically the energy consumed. Yeah, okay. So some prior work. So actually, the closest work that we could find, compared to what we have considered here, the closest work is like on online job scheduling with deadlines. Here you have a server where these jobs arrive intermittently, and each job comes with a deadline. And the server has to like choose which job to process at any time and at what speed. Like power consumption depends on the speed, and the objective for this server here is to process all the jobs before their deadline while consuming minimum energy. And for this problem, under like certain assumptions on the power functions, like for specific power functions, um, certain like competitive ratio bounds have been derived. So I mean, though this problem appears like appears to be close to what we have considered here, but there are some very stark differences. Like the first one is that if here the job scheduling with deadlines, like the deadline is associated with a job. A job comes with a deadline. How, in, while in our case, though we have shown that this peak age of information constraint is equivalent to a deadline constraint, the deadline is associated across updates. So basically, the deadline, what the deadline here means that you need to transmit a new update before this time instant. It does not insist on which update you transmit. If you have multiple new updates, you can discard some of the updates, like we discussed. So as I said, that in job scheduling problem, this deadline is independent of policy, while um, in the problem that we have considered, like the deadline depends on the policy. And also in job scheduling problem, all jobs need to be processed. While here, like in our problem, it is sufficient. It is sufficient to. It may be sufficient to transmit a subset of updates. So the problem that we have considered here, it is combinatorial in nature, and so for this problem, what we do is we propose a causal policy and then bound its competitive ratio, and with respect to optimal offline policy for all increasing and convex power functions. So we don't restrict our result to any specific power function. Like it extends to all, just that the function has to be increasing and convex. Um, and then we will come to what is so special about the bound that we derive. So that we will see. So the policy that we propose is, like we call this as a green tea policy. What it does it at any time t if an update is being transmitted. So it continues to transmit the update at the current rate. It is to say that it never interrupts an ongoing transmission. It neither changes the speed nor preempts the packet. It continues to transmit it. Otherwise, if all of previous like if the previous transmission has completed and now it has to choose which update it should transmit, then it basically begins to transmit the like latest update that it has, and at constant speed, which is given by this function. So what it says that so you choose which update you want to transmit, and then you fix the transmission update. So this is what this policy is doing. Um, so at any time when no update is under transmission, it looks at the latest update and it chooses this speed and begins to transmit it without interruption. When this transmission completes, then again at that point of time, it will look at the latest update and then again compute the speed and begin to transmit that. So what is this special about this speed? So actually this speed is very, like this choice of the speed function is actually very important. So this is as follows. So basically the speed function is like max of these two terms. The first term is basically to ensure that if you begin to transmit an update, you completely transmit it before the deadline. So here the denominator, this is the time before the like deadline constraint will be violated. So this is the time before which you want to complete transmit an update, and this is the size of the update that you want to transmit. So this is the like minimum speed at which you should transmit to satisfy the deadline constraint. And the second term, this basically says that like this ensures that the policy does not spend too much time transmitting a single update. So as we saw, like it may be sufficient to transmit at smaller speed to satisfy the deadline constraint for now. But if you spend too much time doing that, you will have lesser time to transmit the next update. We saw in the previous example that like both are related. So how much time you take to transmit the current update and how much time you will have to transmit the next update. So that is why this second term ensures that you don't transmit like at very low speed. Like basically, yeah, you don't spend too much time transmitting a single update, and there should be sufficient time to transmit the next update. So our main result for this first part is, um, for the greedy policy, we show that its competitive ratio is upper bounded as follows. So it is a function of like the power. It depends on the power function and the ratio of the update sizes and the peak age of information constraint, basically this threshold D. For specific power functions, as we like see, I mean, this is as follows. In first case, when this power function is polynomial, like it is independent of W by D. But however, for the second function, it actually depends on W by D. So is this bad actually? Yeah, I mean, it is bad, but not much. I mean, because we also saw that any causal policy, like uh, like any for any causal policy, the competitive ratio will depend on these quantities. Like will have similar order of dependence on um, the system parameters. So as you can see here, so if say alpha like is unbounded, I mean, though it is not in practice like for such power functions, so like, but it is like has similar order of dependence in both cases. So just to summarize the result, like what we saw in this part one of this talk, basically for this problem that we considered here, the competitive ratio of all causal policies depend on this power function and the ratio of the date size W and the peak age of information constraint D. And then we proposed a simple causal policy that never preempts any packet, never changes speed of packet during transmission. We saw that this simple policy, because of the clever choice of speed function, basically the lower bound that we had in the speed function, that second term, that was actually very critical. You cannot increase or decrease it and get the same bound. So basically, if you decrease it, you will have like unbounded. Like you may have like this was the very like best choice. Like with this clever choice of speed function, you we saw that like we got the dependence of the parameter like like similar to the lower bound. So though we have like discussed this we have given this very brief introduction to this problem. In actual like paper, the journal version of this paper, like in this of this work, you can find like more details. Details in the sense there are extensions of this problem, where we have actually also considered this constraint of the transmission power, the speed at which you can transmit. So that is a more complicated uh, part. So we leave it for now. You can find the details in the journal version of this work. So basically, this constraint on transmission power, it like physical feasibility becomes an issue actually. So that is also an interesting thing, interesting extension. The second is like what to do like when the size of updates is arbitrary. So for this presentation, like we assume that these sizes are fixed, supposed to W bits, but in practice they need not be. So we have discussed that in the extended like journal version of this paper of this work. Now we come to the second part. Um, so we have single source but fixed energy consumption model. So at the source, these updates are generated at arbitrary time instants, and these generation times are revealed causally. So once update is generated, you know that it is generated. You have no information about the future. Also, in this part, like we assume that the sizes or update sizes are arbitrary. Like it can change and it can be different for different updates. Now, since this is fixed energy consumption model, so basically here there's one-to-one relation between the update sizes and the time required to completely transmit it. So for this part, like we will assume that size of an update means the time required to completely transmit. And also because if you are transmitting at a fixed power, basically the energy consumed at rate, we assume that this energy is consumed at a fixed rate C. And the sizes are not naturally, they are revealed at the generation time. I mean, this is not natural, but yeah, I mean, we assume that this is revealed at the generation time. So at any time, the source can like transmit it can transmit any available update, at most one, and it can also preempt the update. So the objective in this part is to minimize the sum of this average age of information and the average energy cost. Um, so what is average? So I mean, last part, like previous part one, we had this peak age of information constraint, like where we wanted this age of information to remain below a certain threshold at all times. Here we relax that, so this age of information can be large, but overall the area under this age of information plot has to be small, and also the average energy has to be small. So basically, we formulate this as an optimization problem where the objective is the sum of like objective is to minimize basically the sum of this average age of information and average energy cost. This is formally given as like follows. And decision problem is at any time which update to transmit or not to transmit because of energy cost. So what are the challenges here? So let's just revisit like the prior works. So we would have like heard of this response time minimization problem, or the latency minimization problem, what we already started this presentation with. So these are all identical. I mean, this is also known as like flow time minimization problem. So these are all kind of identical here. Um, uh, so here, like for prior, it has been like a similar model has been considered. A source monitor pair updates are generated arbitrary time instance with arbitrary sizes, and the response time for each update is defined as the difference between when it arrived and when it at source and when it is received at the monitor. And the objective is to schedule like packet transmissions to minimize the mean response time packets. Like for this problem, the SRPT policy, that is at any time transmit the shortest like packet with shortest like least remaining size for the processing time. I mean, at this policy is known to be optimal. Now, I mean, this seems like quite similar to what I mean. This problem seems quite similar to what we have like considered here. However, again, there are very stark differences. Um, as to begin with, as I described, this age of information is very different than latency minimization. Age of information minimization, like I mean, the same policy that works for one need not work for the other. So the difference here is like response time minimization, all packets need to be transmitted, while for considered problem, it is sufficient to transmit a subset of updates, and the problem is hence is a combinatorial in nature. And because all updates need not be transmitted, so you can actually also control the energy cost. You can drop some of the updates to save some energy. While response time minimization problem, you are like you have to transmit all the updates. These updates have a fixed size, so the energy and it's a fixed energy consumption model. So like energy cost is independent of policy. So I mean, two problems are actually kind of very different. Now it would be like easier to maybe realize this. Um, okay, so because of these differences, what I mean, so as we saw, this SRPT is optimal for response time minimization problem, but because of these differences, this SRPT is actually like it performs arbitrarily bad compared to optimal policy for the considered problem. And this is actually even if we discount for this energy cost, even if we just look at this average like age of information minimization problem, still this SRPT is performs arbitrarily bad compared to optimal offline policy or optimal offline policy. Uh, this can be understood from the following example. So here the heights of these, like say these are like the updates. These heights are their size. So in this considered example, what OPT can do is it can choose which update it wants to transmit at any time. It can ensure basically for these given values, it can ensure that this age of information remain is at most one. While uh, SRPT, what it will do is it will get stuck transmitting all these updates close to like time zero, and hence this age of information can be arbitrarily large for this SRPT. So So an important question is then which update to transmit. So before we go there, so let's just define a couple of notations. So this is update I. So for update I, its generation time is Gi and its size is S sub I. Um, so basically, this generation time for an update is constant. So when it is generated, that is its generation time. But as the update is transmitted, its size decreases. So at any time t, its size is at most S sub I, and we denote it as S sub I of t. So basically, we just need to take away from this slide is there are two notations for update I. Gi is its generation time, and Si of t is its remaining size at, at time t. Um, so as we saw, this SRPT policy, this only it makes decision like only based on the sizes, the remaining sizes Si of t, and it has unbounded competitive ratio. Similarly, we can show that for other policies like LCFS, which only accounts for the generation times of the updates, they also have unbounded competitive ratio. So basically, so what intuitively it appears that what a good policy should do is basically account for both generation times and sizes. So therefore, another policy that makes sense is a greedy policy, which accounts for both these generation times and sizes. So what it does is at any time t for any like new latest like fresh update, it assigns this index like which we call as grade. So grade for update I at time t is equals to this quantity where this g of t is the generation time of the latest update that has been completely transmitted in the past. Uh, so basically what grade is, it is the ratio of the reduction in age of information that will be achieved by transmitting this update divided by the total time for which the update needs to be transmitted. And so the policy is simple at any time. Just look at the update with this largest grade and transmit it. So this appears to be a promising algorithm, but there are problems. So under this policy, what may happen is a large update may preempt small update under transmission. So there is a possibility that back-to-back preemptions and like back-to-back preemptions can happen, and it may happen that no update gets completely transmitted for a long time because before its completion, like another update preempts it other update of larger size preempts it. So the age of information can grow large, and hence we can actually show that this can be shown that uh, this competitive ratio of this greedy policy is also unbounded. So basically we need to fix this problem here. So if for this greedy policy, if we can fix this issue that large updates like should not like do not preempt small updates, then we can possibly get something better. Um, so therefore, we propose this policy called SRPT plus, which works in like two parts. So at any time when an update I is under transmission, it follows SRPT. So what this means is, say update I is under transmission, and if a new update J is generated, and its remaining size, like the size of this new update J is less than the remaining size of update I, then preempt update I and begin to transmit update J. Otherwise, if update J is larger in size, then continue to transmit update I itself. So this is simple SRPT. However, when no update is under transmission, that is you have to choose which update to transmit, begin to transmit. Then, then you follow greedy policy. So basically, for available like fresh updates, like you um, assign this grade and transmit a grade packet with a largest grade. Um, And so what the basically the idea is that uh, by SRPT, by making this using SRPT when update I is under transmission, we ensure that when we begin to transmit an update, it's like the completion cannot be delayed by preemption. Preemption can always preemption will always happen if the new update can be transmitted quickly. Um, so back-to-back preemptions can't happen. So SRPT plus solves the problem that we originally had with the greedy policy. And with this small change, what we can show is like SRPT had unbounded competitive ratio, greedy policy had unbounded competitive ratio. But when we combine these two, we actually uh, see that this competitive ratio of SRPT plus is at most 3. So it's a small constant. So this is a nice result. But note that this SRPT will always transmit if it has a fresh packet. So basically so when no update is under transmission, greedy policy will look at uh, if there is any fresh update, and then it will begin to transmit one of the updates. So SRPT will always be transmitting, and hence this is not good when there is energy cost. So even if there is update, you should not transmit if your age of information is already small, because you do have transmission like cost energy cost. So what we do is to control this like issue, to restrict unnecessary transmissions, we introduce a threshold condition in this greedy policy. So though you have a fresh update, for the update to be transmitted, the update should satisfy certain conditions. Basically, this threshold condition is a condition like which is basically a it takes into account the energy cost, the energy required to completely transmit this update, the current like age of information. Um, so all these things, the size of updates, yeah, and yeah, energy cost and age of information. So all these things are carefully accounted by this threshold condition. So I'm not going into detail. One can look for the details in the paper. Um, yeah. So this is the idea basically. The threshold conditions controls whether to transmit or not. Which update to transmit, that is controlled according to this uh, index that we call as grade. And this is very important to actually limit energy cost. Um, Yeah. So with this introduction of threshold condition, we see that so we already had this feature that SRPT plus had competitive ratio at most 3 when there was no energy cost. So this feature is preserved. Additionally, if there is energy cost, even in that case, this competitive ratio SRPT plus is at most 5. Okay, so what we saw that we considered an online scheduling problem where the objective was to minimize the sum of age of information, average age of information, and average energy cost. And we saw that this problem is challenging because of this combinatorial feature of the problem. And we analyzed it for the worst case scenario where both the sizes and arrival times of updates can be arbitrary. And we saw that policies such as this SRPT, LCFS, or greedy, I mean, they have unbounded competitive ratio. But by taking a careful combination of SRPT and greedy and adding a threshold condition, we saw that we got this SRPT plus policy, which has competitive ratio at most 5. So, okay, so this was it for the second part. Next, we go to the third part, is which is about multiple sources and fixed energy consumption model and centralized setting. So basically, there are multiple sources. All at each source, updates are generated intermittently. We assume that the intergeneration of time of updates at a source follows some general distribution. Uh, as this distribution can be different for different sources. Um, but for a source, these intergeneration times are independent and identically distributed. So each source wants to needs to transmit these updates to the monitor. Uh, So consider a wireless system like wireless channel where so the time required to transmit an update is actually like again random. So for update for a source L, again this transmission time, the time required to transmit an update is random, and it follows a distribution DL. So again, this DL can be any general distribution, and this distribution again can be different for different sources. At any time, at most one source can transmit. So this is centralized scheduling. There is a centralized scheduler which chooses at any time which source can transmit, and at any time, at most one source can transmit. And this is fixed energy consumption model. We assume that for each update transmission by a source L, the source there is a fixed energy cost CL. So note that the energy cost does not depend on time for which update is transmitted. Rather, in this model, we assume that there is a fixed cost per update that is transmitted. So total energy consumed for like transmission by a source is proportional to the number of updates that it transmits. But note that the cost is the energy cost is different for different sources. So the cost is same for every like update for of one source, but it is different for updates of different sources. Okay, so the objective is to minimize the weighted sum of this average age of information of sources subject to a constraint on the average transmission cost. This is given as follows. So basically you take a weighted sum of the average age of information of different sources subject to a constraint on the total like average transmission cost. Transmission cost, that is energy cost. So basically CL is the cost per transmission for source L. RL is the number of updates that source L transmits per unit time. And this is a fixed constant. So the decision problem here is that at each time which source gets to transmit and which update the source should transmit such that uh, such that the cost is optimized, like this weighted sum of age of information is minimized subject to this transmission cost constraint, and this has to be done using only causal information. You don't know when the updates will arrive in future or how much time that update transmission will take future. um, uh, so uh, so related to this, like there are like certain works that have been like considered, like so certain works have considered similar I mean similar problems. However, they have been limited in certain aspects, such as transmission cost has been considered in similar models, however only for the single source setting, and even there um, a new update was assumed to be available at all times. So in basically that model assumed that the intergeneration time of updates is basically close to zero. That is to say that you have a new update at all times, like whenever you want to transmit. So for this, under this assumption, for a single source, um, uh, an optimal causal policies has been like derived. Um, for multiple sources, mostly the closest work we found, I mean, they did not consider transmission cost. Um, so the closest we could find is by Cadota and Modiano in 2019. So they considered similar model. However, there was assumption there was no transmission cost, and the update intergeneration time and transmission delay distributions were assumed to be geometric. And for that model, they derived competitive ratio, causal policy risk competitive ratio at most 4. In this work, we consider continuous time setting, and we have considered like general distributions, GLs and like TLs, which can also be, which also Discrete time setting is a special case of this general distributions, basically. Like geometric distribution is a special case of this general distribution setting that we have considered. Also, there is non-negative transmission cost, so sources can have like cost for transmission. So for this setting, we proposed a randomized scheduling policy and upper bounded its competitive ratio. We showed that this competitive ratio is independent of the transmission delay distributions and only depends on the ratio of the variance and the mean square of the update intergeneration time distribution at the sources, and which is at most one for several common distributions such as exponential, uniform, and Rayleigh. So basically, for these distributions, this competitive ratio is at most 4 for the proposed policy. Further, we showed that for this proposed policy, the analysis is tight. That is the dependence on this variance and mean square. I mean, that is unavoidable for this policy. Yeah, so for this policy, this is the limitation. Although, like, we don't know if optimal policy also depends on this distribution GL. So next we come to the policy. Basically, the proposed policy operates has two subroutines that run in parallel. One is the update selection part, which chooses at each time, at each which is used at each source to choose whether an update that is generated is worth transmitting or not, given the transmission cost and the age of information, current age of information. And the second part is source selection, which it chooses at any time which source gets to transmit. So for update selection, basically at each source, whenever an update is when at source L, whenever an update at source L, whenever an update is generated, so it marks the generated update with fixed probability PL, where this PL is found by minimizing an upper bound on the cost. And so what this basically means is the update is marked with probability PL, and with 1 minus PL, it is not marked. And if it is not marked, we basically discard it. So yeah, with probability PL, update is marked. With 1 minus PL, it gets discarded. So whenever source L is selected to transmit, it transmits the latest marked update. So this is the policy. So it is important to mention that, okay, so this appears simple to choose which update to transmit. But this actually the most complicated part is consumed like is hidden behind how this PL is actually is chosen. So basically computing PL is easy, but the intuition there is actually it takes into account all the parameters of the system, different at different source at all sources in the system, transmission distribution as well as the update intergeneration time distribution of all the sources, and also the energy cost for all the sources. Then second part is source scheduling. Here for each source cell, we define a probability QL, which actually depends on how frequently the updates are marked at source, and we that normalize it is QLs for each source such that their sum is equals to 1, and the algorithm is like simple among all sources. Schedule source L with probability QL. So to pick a source L with probability QL to transmit, then the source L will look at all the marked updates that it has and begin to transmit the latest marked update. So this policy never preempts any update. So the intuition is, again, just to recap, the intuition is as follows. So this update selection part, this marks an update eligible for transmission at source L with probability PL. This where this PL is obtained by minimizing an upper bound on the cost, and this PL actually takes into account all the parameters in the system. And this update selection is important to manage transmission cost, because what the source scheduling does is it controls the frequency at which a source gets to transmit its mark update. Now, whether or not to transmit, that is decided by the source to overall control the transmission cost. Okay, to summarize, so what we saw in this part 3, we considered a general setting with multiple sources and arbitrary update generation time and transmission delay distributions, and also like fixed transmission cost. We proposed a novel two-stage like randomized policy and upper bounded its competitive ratio. We showed that its competitive ratio is independent of the transmission delay distribution, and is at most 4 for several like common distributions like exponential, uniform, and Rayleigh. So that was it for part 3. Next we come to the last part of this talk, that is part 4, where we have multiple sources, fixed energy consumption model, and decentralized setting. So basically in a decentralized setting, you don't have a centralized scheduler. Each source chooses on its own when to transmit, and without knowing the knowledge of other sources. So basically each source is in its own bubble, so it does not know about other sources in the network. And simultaneous transmission by multiple sources cause collision, due to which all transmissions fail. So for this problem, we consider slotted time setting. So a new and also we assume that a new update is generated at each source in every slot. So slotted time. So in each slot, an update is generated at a source, and the source needs to decide whether or not to transmit. So if and there is transmission cost CL for source L. For each transmission, the source L, so the source L incurs transmission cost CL, and if there is no collision, the transmission is successful in the same slot. That is, the update is received at the monitor in the same slot, and the age of information of the source decreases to 0. Otherwise, there is collision and all transmissions fail. And the self is objective. So a source does not know about other sources. It just means like it just needs to minimize its own age of information while incurring little transmission cost. So now note that um, when there is collision, you do incur transmission cost because you have actually transmitted, but there is no reduction in age of information. So one thing that is obvious for achieving this objective for a source is to minimize collision. So it is critical. And in past, like a common strategy to avoid collision is to follow a backup strategy. What is that? So when there is collision, you wait for a certain time before next transmission. So you don't transmit immediately. So this is what backup strategy generally is, where this time differentiates different algorithms. So how much time you wait, that differentiates an algorithm. So a famous backup algorithm is exponential backup. So what it does is in each slot, it transmits with probability pi. If there is collision, you decrease the this probability by half. So in next slot, you will transmit with a half probability. Otherwise, you slightly increase the transmission probability. So you transmit more aggressively if your transmissions are being successful. So what are the challenges? So challenges are like there should exist an equilibrium among the sources. So after a while, like all sources should converge to a certain probability where they can operate in equilibrium, basically. And the equilibrium should also balance the age of information and transmission cost for the sources. So it should take into account the trade-off. So it should not be like the transmission cost is growing unbounded large. So the trade-off has to be accounted for. So exponential backoff, as I said, it does not work for the considered problem where we have age of information. So why is that? Because the transmission is, say, a transmission is successful in slot I, then the age of information is slot I plus 1 will be small because just a new update has been transmitted. So even if there is no collision, less chance of collision, you should not transmit in slot I plus 1 because of transmission cost, right? But what exponential backup does is, it when there is transmission like success, it increases the transmission probability. So this is obviously a bad idea. Um, so this policy is not suitable for this considered problem. And hence, as a system designer, we need to find another algorithm that is suited for this considered metric. And hence, we propose a learning algorithm and show that it meets all the requirements that we are looking for. Basically, the algorithm is as follows. We have a slotted time, and so we group like this. We partition this time axis into frames, where each frame consists of m consecutive um, time slots, and each frame has equal number of slots, that is m. So at source L, in each slot of frame T, we transmit with the packet that is generated in that slot with a fixed probability PL of T, right? So, and how is this PLT computed? This depends on the previous frame. So basically, so you initialize the algorithm with some probability at the start of frame 1. Then in each slot of this frame, the source transmits with this probability PL of 1. And at the end of this frame, it computes PL of 2 based on the average age of information and transmission cost incurred during this frame. And this update is done as follows, where you have this current transmission probability. You add to it a certain, basically a quantity that is a difference between this current transmission probability and a function which function of age of information and transmission cost incurred in frame T. And then again, you in the next frame, you transmit with this probability PL of 2, and then again you compute PL of 3, and you transmit with this probability in frame 3, and so on. So I am not going into the detail of this function, but basically this function, it consists of two parts. Basically, this first part increases with increase in average age of information, while the second part decreases with increase in average transmission cost. So this sum actually increases if the average age of information increases, and however it decreases if there is increase in average transmission cost. So that is how it actually captures the trade-off between age of information and transmission cost. And obviously, while designing these functions, like certain trade-offs have been like these functions have been like, it is not any just increasing and decreasing functions here, but they have been taken carefully such that we get the desired properties that we want. So this function basically decides whether to increase or decrease the transmission probability depending on the relative values of average age of information and average transmission cost incurred in latest frame. Okay. So for this algorithm, the learning algorithm that we just saw, the main result is that if all the sources in the system follow this learning algorithm, then their transmission probabilities converge to a unique fixed point. And so basically these sources can work in equilibrium, but most importantly, this fixed point adapts to the number of sources. So basically it takes into account if there are larger number of sources, so it transmits with a smaller, the fixed point, the transmission probability of sources will be small. If there are fewer sources, the equilibrium transmission probability will be large. because when there are fewer sources, there is less chance of collision. While if there are larger sources, there are larger number of sources, there is more collision chances of collision. Um, and also like the convergence is guaranteed for any number of sources. So how do we show this? We basically for this we follow an inverse game strategy approach. Basically, we define a non-cooperative game where there are n players. Basically, the n sources correspond to n players. So remember that this n is not known here. For to like is not known, but we assume that there are say n sources, and each source acts as a player. And the action is basically the probability PL with which it transmits, and the utility function is it is basically a function of the transmission probability of like all the sources in the network. That is that for a source L, the utility function is a function of the probability with which it transmits, the probability that no other source transmits, and its own cost per transmission source L. And this utility function actually captures, we have shown in the paper, it actually captures the trade-off for this source. Basically, if this cost is large, the utility function it captures the trade-off between transmission cost and age of information. So how do we prove the result? We basically show that this learning algorithm converges to the best response strategy of this game, and this best response strategy of this game converges to a unique Nash equilibrium of this game. So this is how we show that this learning algorithm actually converges to a fixed point, which actually is the Nash equilibrium of this game that we have defined here. So so just to recap, so what we saw in this part, that we basically propose a decentralized algorithm that each source can follow on its own, locally, based only on its own average age of information and transmission cost incurred in past. And when all sources follow this learning algorithm independently of each other, their average age of information transmission cost converges to a unique fixed point, this convergence is guaranteed for any number of sources. So to conclude, basically, we saw this age of information metric for in this whole presentation. We saw that age of information metric for information freshness, and we considered age of information minimization problem. And we saw that not all updates need to be transmitted. So that is why this age of information minimization has this combinatorial feature, which makes it different and from prior work, and has its own challenges. So this needs to be given due importance. And so we saw that different decision problems for obtaining information freshness. So these problems differed in the different models, such as based on energy consumption or the type of scheduler. And for each of them, we designed a causal algorithm and derived theoretical performance guarantees. And but most importantly, what we did was we developed several key intuitions and techniques for the design and analysis of such algorithms, which we believe will be of much use for further sophisticated problems as well. So thank you. So this is the end of my presentation. So while doing this work, we also got certain lot of these results that I discussed here. They have already been published in journals. So they can be like found online or on my homepage as well. So if you're interested, please refer to them. So these papers do have a lot of details. Uh, for ease of exposition, I have obviously I have uh, like taken away a lot of details. So please feel free to read these papers if you find the problems interesting. Um, Thank you.